Okay, I just want to do an example here of which basically demonstrates the powerfulness or the usefulness of the central limit theorem. The thing here is that we've got some data relating to a sample of 90 students, and the mean and the standard deviation, the distribution of weights where they enroll, is presumed to be 7.5, the standard deviation, and the mean of 70. And that's from previous kind of experience here or whatever, that we know the standard deviation and that previously the mean is 70. And now a random sample of 90 students from a new entry is weighed, and the mean is somewhat more. And the hypothesis is that that there is evidence that the mean of the new entry is more than 70 kilograms. So we've got a one-tailed test, but the thing here, it doesn't say anything about the parent distribution at all. It doesn't say it's normally distributed. That's what makes the importance of the central limit theorem really key here, because the central limit theorem can be used for the question, which is basically what's going to be the answer to part B. So let's go on with the question. Okay, it's quite good to define our parameters normally. So we let mu be mean of weights of students of new entry. Right, now the null hypothesis, it's the same as it's always been, so mu is equal to 70. But the alternative hypothesis is that mu is greater than that. We think that this new entry is bigger, and it's all in the word in the question. New entry is more than 70 kilograms, and hence one-tailed. Okay. So the central limit theorem, basically, if we let x be equal to the mean distribution of means of 90 samples of size 90, distribution of means of sample size 90. Okay, right, now therefore x will be normally distributed with mean mu. That's really part of the null hypothesis, really, but the mu is unchanged. So thinking about it, I might shove that above I might actually put this below. I don't think it really matters, but it just seems to make more sense to me anyway, if I shove this a little bit lower down to here, because I've defined a distribution in there which makes a bit more sense, at least it does to me. I don't think it matters too much, but the point here is, because it's a sample of 90, we've got a variance of square root of over 90, but we know the variance. That's not going to be changed. So the variance is 7.5 squared for the original distribution. So the variance of the sampling distribution will be 7.5 over 90, which means the standard error basically the standard deviation of the sampling distribution is 7.5 over the square root of 90. Okay, and this is where the central limit theorem applies. It is approximate, so I may be, I could, especially with a sample size of 90, it is approximately normally distributed with sample size of 90. Okay, so let's get on and do the test. So you should recall that the way we conduct these tests, or the way we've normally done, is we normally transform it to use the transformation to the standard normal distribution, and we use this as a test statistic, which is equal to our value of the sample means, take away the actual mean of the parent population, divide by the standard error, or the standard deviation of the sampling distribution. So that's what we use as the, well, let's just put the general case in. So this is what we use as our test statistic. So in this particular case, we have, and going back to the question, 71.6 as the actual value of the mean that we found from the sample that we've been given. 71.6. Take away the mean 70 divided by the known standard deviation presumed to be unchanged, divide by the sample size, and that equals to 2.0339. So then we compare those with the critical values of the standard normal distribution, and you can find these critical values on the calculator. You put in something like 0.95 on the inverse on your calculator. You put in 0.95 because we want a 5% significance level. 5%, and so you put in 0.95 in inverse normal. Of 0.95 for the standard, and remember by using this we've transformed it to the standard normal distribution with z equals mean of 1 and standard deviation of 1 squared. So that's how you can find that number, and that number you will find, make sure you can find it, is 1.6445. So we've got 1.6445. And any number in here, we're going to, this is like our critical region, any number in there, we're going to reject the null hypothesis. Well, we can see, and I'll write it here, we can see that our number is actually greater than our critical value. Okay, 449, or 449 it should be, never mind. 5 significant figures, quite over the top anyway. 1.6449. So it's greater than that. So in other words, we are in the critical region here with our value of, let me write this again, that's 1.6449 is the critical value there. But we're somewhere in this is our test statistic, value of our test statistic is in here. Value of test statistic is in critical region. I'm probably writing more than I need to answer this question, by the way. This would probably be enough, critical value, but I think it's good to back up with a diagram. So value of test statistic. So therefore we can reject the null hypothesis. So we reject H0, and then we need a contextual statement with some reference to the fact that it might not be right. There is a 5% chance at least, or at least, well, maybe the actual significance level is better than 5%, but even so, there is a chance that our null hypothesis is incorrect. So we have to give some, reference to that, some nod to that. And the way we normally do that is say there is sufficient evidence to suggest, that kind of, that's pretty well covers it. And let's get to the original question. The original question said that the mean of the new entry is more than 70 kilograms, to suggest that the mean of the new entry is more than 70 kilograms. Okay, and that is basically the answer to the question. I notice some people are writing, and some teachers get their students to state the significance level in here. Strictly speaking, you should, but looking at mark schemes on all the major exam boards, they don't seem to require it, so I haven't written it here. But anyway, that's that for that part question. And then just to ram home the point about the central limit theorem. It says state the importance of the central limit theorem to the test, and we can just say, because you can just say, even though parent distribution is not known to be normal, because the sampling distribution, because the sample, sorry, is large. Certainly 90 is definitely pretty large. It can be assumed, or the sampling distribution can be approximated to the normal distribution. Can be approximated to a normal distribution. Using the central limit theorem. Okay, that's it. So actually, for those doing this as part of further maths, and I think all of the boards will have this in further maths stats course, you might recognise this in single maths as well. I suppose the difference, the reason why this couldn't come on a single maths paper is simply because of the fact of it not being normally distributed, or not necessarily normally distributed, and therefore we need to use a central limit theorem. But the test itself is something that, if you've been looking through the examples on single maths, the stats part of that, is something we should be familiar with, using this as a test statistic. Okay, that's it. Hope that was useful. Bye.